Hello, and I'm back, and I want you to think about unit number 2 when we were talking about different planets in our solar system, and then we went on to talk about different planets in our galaxy. And one of the things that we made use of was Kepler's third law of motion, and that was that whenever you've got a star and then you got a planet that's going around it, there would be a relationship between the distance from the star to the planet, and then how long did it take to go around, and then also the mass of the star plus the mass of the planet. So it was all related to each other according to that formula there. So that's equation 5.10. And then we also talked about the concept of center of mass, that really the planet is not going around the star like this, but they were actually going around each other, so that the star and the planet were in orbit around each other, around their common center of mass. Now, if you've got two objects that are the same size, then they basically revolve around each other, around the midpoint. But as this object over here gets bigger than this object over here, then what you find out is the center of mass gets closer to this big object. And in the case of the sun, it's very difficult to even notice that the sun is moving, but it actually is just a little bit. So the sun is actually going around in a circle around the common center of mass between it and a planet out here. Now, what do you notice though? So what you notice, if you've got two relatively large objects such as a binary star system, so we're talking about two stars that are in orbit around each other, so that means that they're relatively big. So what you would notice is that this star would be wobbling. It would be going back and forth because it's actually going around its center of mass. So we have some additional formulas that I've listed there, which you don't need to worry about, okay? I just like to show you where all of this stuff comes from. You're not going to be doing any calculations of center of mass if you're one of my students for the exam. But I just want you to know what's the concept of the center of mass, and the idea that if you've got a binary star system, they're both in orbit around their common center of mass. Now, how could we use this in order to figure out the mass of a star? So that's our ultimate goal, is to figure out M, the mass. So here's a sample calculation. And so we're assuming that we're able to measure the distances to the center of mass by using geometry and trigonometry. So like, for example, let's say that here is Earth. Okay, here's this binary star system up here, and those two stars are in orbit around each other. Now we can figure out the distance to them by using what method? Parallax. Okay, you remember the parallax method. So we know the distance to them, and then we look through our telescope and we can actually see the wobble of this thing. So we can measure that wobble, and we can use some trigonometry on it. And so we can measure this angle right here, and we know this length. So by using trigonometry, we could figure out this. Let me just call it R sub 0. I don't know. So we'll call that R sub 0. So it can be done. We can use, from mathematics, trigonometry, to actually measure this little distance here. And so that's what's given in this problem, that we have measured the amount of time it has taken for these two things to go around each other. That would be the period. And by using trigonometry, we've measured the distance for that center of mass. So our first step is to plug into Kepler's third law. We know the period, that's the T looking thing, and we know the R, so we know this thing, and we plug that in, and now we can figure out the total mass of the two stars, okay, the total mass. That's still not good enough. We want to know what's the mass of just one of those stars. So then the next step is to use the concept of center of mass, which I do there, and then now you've got two equations and two unknowns that you can solve, and now you can figure out the mass actually of each one of the two things that were going around each other. So I just want you to know it can be done, and I want you to have a general idea for how do they do it. But you're not going to be doing actually physical calculations on the exam. Well, astronomers have done this for literally thousands of stars, that they have measured the amount of the mass of stars by using this technique, and by looking at the star, they have measured their luminosities. Now, how do you get the luminosity again? You put your photometer on your telescope, and then that gives you the F, the apparent brightness. You know what the R is, so you put both of those numbers into the photometry equation, and you solve it for L. So astronomers have measured the luminosity of thousands of stars, and they've also measured the masses of thousands of stars, and then they graph it. So look at that graph there. Notice that it falls on a pretty much straight line. So that tells you there's a relationship between the mass of a star and the brightness of a star, which you would expect, because the more massive the star, the more nuclear explosions it's going to have, and the more nuclear explosions it has, the brighter the star is going to be. So there's a relationship. So what does an astronomer do? So all they have to do is measure the luminosity of the star that they're interested in, find that luminosity on the up and down part of that graph, and then go sideways, bounce it off that line of stars, and then go down, and now you know what the mass of that star is. Pretty impressive. Okay. So, and again, how did we get the luminosity? Remember, dominoes. So you got the luminosity from back here, finding the luminosity by using the photometry equation. And how did you get the R? Okay, so you get the R from back here. So it's a whole bunch of dominoes. If you know the R, then you can calculate the luminosity. And now that you got the luminosity, you can use it to calculate the mass of a star. Pretty cool. All right, another thing that we can measure is temperature, and we'll do that in our next segment.